happy to be here today and to have the possibility of talking to you about hybrid algorithm for machine learning, and in particular discuss some application in the financial sector, and in particular also put forward ideas on how we could, let's say, design this application in order to show quantum advantage. I would like to start by introducing a little bit Cambridge Quantum Computing. So we are an independent quantum software company and technology provider, around 90 people globally, most of them researcher, and most of them with a strong academic background. The main R&D teams are in the United Kingdom, and we have BizDev offices also in the US and in Japan. We are a science-first organization. We do a lot of research, and then we partner up with the top industry player in oil and gas, pharma, chemical, healthcare, and finance. These are some of the engagements we have in order to develop, let's say, early-stage application and to help this organization to plan for the quantum future. We also have strong ties with, I would say, the top academic institution and research institution across the globe. What is it that we do specifically? So we do a little bit of hardware. Let's say here we build Iron Bridge, which is a device that uses 4 qubits to amplify classical randomness and certify, the quantum nature of this amplified randomness. The rest of the team and most of the researchers are focused on software application, though. So the two main application team are the quantum chemistry team based in Cambridge, and my team, machine learning and quantum algorithm, based in central London. And then, let's say, we have a core team that develop Ticket, our software stack and compiler. So all our software applications are built on top of Ticket, and what Ticket does is that it's basically a compiler. So it allows us to write our software using, for example, Qiskit, Cirq. I think Q# is supported as well, the Rigetti programming language. And then Ticket takes care of optimizing the logical circuit for the specific instance on the quantum computer of one of these providers, and optimizes the circuit so that, in very sophisticated way. For example, it's aware that some qubits are better than other connectivities, so that, our application are basically have a nice chance of success and less corrupted by noise, and makes, let's say, the whole prototyping work much easier. I will just talk a little bit about my team, the machine learning and quantum algorithm team. We are an R&D focus group, and we research quantum algorithm for optimization and machine learning. We publish scientific research, then we translate this research in proof of principle implementation on NIST devices, and then we tailor this implementation for our industrial partner. We adapt it to their data set, and we make our software relevant for their business problem. It's a nice interdisciplinary team. Most of us has PhD of postgraduate experience. I have, PhD in deep learning, postdocs in signal processing. I'm a computational condensed matter physicist. We have people that have studied extensively in error correction and in the, for example, in this quantum physics methods such as tensor nectar applied to quantum circuit. And that's, that's the end of my introduction. So let's move on to the interesting part. So I mentioned that I will be discussing ideas on how to develop application with the potential of chasing quantum advantage. Why should we do that? Well, maybe from the point of view of a theorist, of scientists, that's obvious. But in businesses, instead, there is a lot of interest in developing quantum application, but it's not always clear how to do it in order to really make the most or design thing in a way so that we can experience quantum computing at its best. So it's great to experiment with quantum computer. It's even more exciting if we do that in ways that show that quantum computing can outperform anything that we have in the classical computing so far. So this concept is called quantum advantage. It's linked to quantum supremacy, and I want just to discuss the link between the two because, of course, we had John Martini speaking earlier, and he gave a great talk. So these are not definitions, it's just really to put some meaning into words. One could say that an algorithm can prove quantum advantage by beating anything classical that we have so far. It's a sort of, but not necessarily. I mean, this doesn't mean that there are classical algorithms in the future that couldn't do better. But it's simply a strong proof that quantum computing can do things better and with less resources. Quantum supremacy instead is being capable of running an algorithm that solves for the first time a problem that we couldn't even dream of solving with classical computing. Even in extreme case scenario where the human civilization reaches such a level of technological advantage that, for example, can harness and exploit all the energy produced by the sun and channel it into a classical computer. We know that there are problems that even if we were able to do that, cannot be solved using classical computer, and only quantum can do that. So quantum supremacy was demonstrated. I won't repeat what John Martini said, but the point is that a paramount technological and hardware challenge was overcome, and basically it was demonstrated that we are capable with a specific hardware type of running proper quantum programs that are not corrupted by noise. It demonstrates that this hardware is within the bounds of error correction, and in particular that it shows that, it gives us the strong indication that this type of hardware should be capable of running those algorithms that promise exponential speed up. This is amazing. What does quantum supremacy mean for algorithm developers? So when it comes to algorithms, there are, roughly speaking, two classes. So one are, let's say, we call them pure quantum algorithms. So quantum algorithms where all the information is loaded on a quantum machine, processed, and then we read out the solution to our problem, right? HHL algorithm, Shor algorithm are this kind of type. They it's guaranteed by the theory, exponential speed up, but they require almost perfect machine. Basically, they require error correction. So for this type of algorithm, quantum supremacy means that error correction is one step closer, but the point of error correction is that error correction will be a step change. At some point, we will have it, and our quantum machine will be amazing. We'll be able to run, again, sort of general purpose quantum program, but it will be a step change. The algorithm I'm going to talk about today are hybrid quantum algorithm, where there is a tight and frequent exchange of information between classical and quantum computer. This kind of hybrid, hybrid algorithm, they trade the guarantee for speed up for robustness by turning our quantum circuits into variational circuit and parameterized circuits, and by using a classical computer to tune the parameter of this circuit. These systems are robust, and we can use them today to experiment with quantum computing. But more interestingly, because of this characteristic, they can take advantage of very little improvement in the hardware. Every qubits, but most importantly, each small improvement in the quality of the qubit here can be exploited to run deeper circuits and to have, let's say, better answer and solution to our problem. So I will describe you which are the three main components of an hybrid algorithm. So the first important block is the parameterized quantum circuits. Here you can see a schematic. So there is the classical information that flows into the quantum computer and is encoded by an encoding circuits here. Then once we have our data set on our quantum computer, there is the variational circuit here that has parameters that can be implemented as our machine learning model parameters, the ones that are tuned during the optimization process. The circuit structure of both blocks, and the type of gates that are implemented there, it's ad hoc and has to be chosen to fit our specific instance of the problem. This kind of algorithm, then the information is then read out and post-processed for recovering the answer to our problem. This type of circuit are widely applied in state-of-the-art NISQI application in machine learning and optimization. I would like just to mention that with my team, we published this review on how to use parameterized quantum circuit for machine learning model, and we are more than welcome to have a look at that. So this is the first component of our hybrid system. The second component is let's say, the hardware component. So as I said, there is the readout from the quantum computer here is then processed by a classical computer, and the classical computer tunes updates the parameter thetas of our quantum circuit. And this happens many, many times. So why do we like CPUs? Because they are fast, fault tolerant, they can handle a lot of data. Why do we study quantum computer? Because it can run quantum programs that are hard to simulate or impossible to simulate classically. Quantum supremacy / quantum advantage. And especially if we think about machine learning, there are theoretical results that prove that, let's say, certain circuit can be, are analogous to deep neural network and are more expressive compared to the classical counterpart. So the idea here, let's outsource the manual and repetitive tasks such as updating the parameter of our quantum model on the classical computer because they are very reliable machine. And let's keep the machine learning model on the quantum computer because we know that quantum computing can achieve more compared to classical one. So the key point here is that the hybrid system is not fatally compromised by noise, faulty operation, and limited size. The last ingredient of our hybrid algorithm is the optimizer, the parameter optimizer. Here there are many nice connections that can be drawn between parameterized quantum circuit and deep learning. We can tune this parameter with gradient-based method. We can run the same circuit twice to get the finite differences, finite difference gradient, let's say, of our cost function. We can run quantum circuit to get the analytical gradient. We can even exploit the intrinsic noise of these devices to run quantum version of stochastic gradient descent. That's quite interesting, I suppose. Or we can use, especially for unsupervised learning, you can use gradient-free optimizers, right? The key aspect there is that some fundamental components of deep learning, such as backpropagation, because of things like the non-cloning theorem, they're not straightforward, or it's not obvious on how to do backpropagation on a quantum machine. So there are many interesting technical questions to address. We need novel optimizers. We need to think of proper initialization for the parameter. There is a lot to be done. So yeah, this is, let's say, the third component. So the first component of the parameterized quantum circuit. The second one is this classical quantum data loop. And then the third one is the optimizer for the parameter of the model. So application to finance. OK, let me just spend a couple of minutes to give a motivation, right? The typical answer when you speak with people interested in application is, why should we do it? This sounds a bit, it's a high-level approach, but I think that there have been compelling arguments have been put forward in finance and quantitative finance to develop new models that are more articulated, that can make sense of situations that are rare but potentially quite critical, and most importantly, data-driven. How does quantum computing fit in here? So quantum computing, we know that offers a new way of process data, so more efficiently, and offers more powerful, more expressive models. So I think there is a fit here. But the key question is, where do we start, right? How do we marry the theory, let's say the quantum part, with the practitioner view? So, and I think the right way of doing this is to focus our resources on algorithm and application that have a promise of an indication of quantum advantage. So quantum finance, it's probably a relatively old concept. As you can see here, there is an Austrian banknote with the face of Erwin Schrödinger here. But the reason why I like it is that it's a mathematically rich domain. And financial practitioners, they look at data, they try to abstract the problem in a mathematical form, and then they look at algorithm how to solve the problem. So I think that the mindset there of the practitioner is quite is the right one, and we can look at the classical solution and then quantum enhance them. I'm going to discuss three main applications. I'm going to discuss unsupervised learning for stress testing and generating financial data, portfolio optimization, discrete portfolio optimization, with the quantum approximate optimization algorithm, and then how to accelerate the convergence of Monte Carlo sampling for option pricing. So let's start with the first case. So scenario simulation. Why should we think about this? Because in finance we know that although there is a lot of data generated every day, and a lot of data, I mean, many terabytes, generated by each single exchange every day. There are always, let's say, peculiar, potentially risky situations that happen once in a while and could have very drastic consequences on the global financial market. Sometimes the data for these special scenarios, special cases, is very scarce. Another case is that if we had a nice like market simulating machine, we could just adjust the knob of this one and test our portfolio, our asset allocation and make sure that these choices are robust in all the scenarios. The third case is that these algorithms such as reinforcement learning are becoming quite popular, especially in market making and liquidity provider, and they're very data hungry. So there are studies in the literature where classical generative modeling is being used to generate more data for reinforcement learning. So which tool can we pick from our quantum toolbox to solve this sort of problem? I will be brief, but I'm quite excited about the quantum circuit Bohr machine, which is a generative model which have been developed also with the collaboration of a member of the CQC team, and I'm talking here about Marcello Benedetti. And there are three main points here that I want to make. I don't want to enter into the details. We can talk about this later. But it has been theoretically proven that quantum circuit Bohr machines are more expressive than comparable models, such as, for example, Boltzmann machine. That's the first point. The second point is that these models cannot be simulated efficiently using a classical computer. And the third point that is generally true for a generative modeling, there is not, basically all the data stays on the classical machine, and that's very good. We don't have to transfer a big data set on the quantum machine, basically. Yeah, I think that this is very exciting. But let's move on to the second case. So portfolio optimization. So portfolio optimization is a case of a finance problem that has many kind of mathematical, can be modeled in different mathematical ways. So it can be modeled using stochastic partial differential equation. There are recent work involving CQC collaborators where you can use variational circuit on these devices to solve system of equations. This is being done for equations that look a lot like the Schrödinger equation. So here the question is, can we twist a little bit the problem to make it look like a Schrödinger equation and then use this algorithm that have shown an advantage, right? Another way to model this is treating the problem of picking good portfolio as a convex constraint optimization problem. Here we have, in the quantum algorithm world, we have, for example, quantum semi-definite programming, which guarantees an exponential speed up, proven that we can prepare the state of the quantum computer in a special way, let's say. There are some challenges here. Again, at CQC, we are looking into this, but that's an interesting point of view. I would like to focus, though, on the last case where we make our portfolio allocation discrete, and therefore, when your portfolio is discrete, the problem of picking the right allocation becomes a combinatorial optimization problem. This class of problem of this equal to solve on classical machine. The best the classical machine can do is to use heuristics to basically find good approximate solution, but not in an efficient manner, let's say. This is a hard computational task. So the point here is, why don't we try to develop some quantum heuristic to do the same, and perhaps something good will come out of it. So to do this, we can use, for example, quantum approximate optimization algorithm, or a more general family, which is called quantum alternating operation ansatz, which, basically speaking, they're not guaranteed to find a better solution, but often they can do it in practice. In particular, it had been proven that QAOA algorithms in specific computer science problems are systematically better at finding a solution to this specific, again, some specific combinatorial optimization problem, which is a good thing. The tricky point with this variational circuit, they have a lot of parameters, and they're within the grasp of these devices, but still quite computationally intensive, is that implementation is crucial. You need to have a good compiler, and you have to have clever and ad hoc way to choose the parameter of the circuit. Okay, so moving on to the last case, option pricing. We know that, again, it's similar to portfolio optimization because it can be modeled in many ways. We know that we can use the amplitude amplification algorithm to speed up the conversion of basically the expected value of the option if we decide to model the option price as a stochastic system. Unfortunately, amplitude amplification requires many qubits and deep circuits. But very interestingly, researchers have found that using a variational circuit, we can approximate the amplitude amplification algorithm and still recover the quadratic speed up promised by the full amplitude amplification algorithm. So basically, we can use variational algorithm to approximate this more the full-fledged quantum algorithm. The pros are that we need fewer qubits to do this, and in particular, number of qubits become a parameter. We can kind of fix that or keep increasing it until the problem is decently solved and within the grasp on these devices. The circuit depth is reduced, and most importantly, we get the same speed up as the full-fledged algorithm. The tricky part, as I said, is that there are parameters that have to be tuned, and the implementation is critical. So moving on to conclusion, really what I would like you to understand from this presentation is that with each example, I discussed and put forward a way of looking and planning for quantum advantage. So in the first case, the case of the quantum circuit board machine, is the case where we can make theoretical connection between classical methods and quantum methods, in particular in this case using tensor network, and prove theoretical that if implemented correctly, our quantum circuit board machine is superior to classical generative models. The second case instead was a case where we have a hard task, no hope to solve it efficiently on a classical computer. Let's throw a quantum heuristic at it, because in some cases, this works very well and shows a quantum advantage. The third case, instead, is where we have a very powerful quantum circuit, unfeasible in the NISQ era, that is being approximated successfully, recovering the speed up. So these are three potential avenues, I would say, for finding application-based quantum advantage. Looking at the future, I would like to say that NISQ computers actually work. We can work with them on specific application, and hybrid algorithms are good. In particular, quantum algorithm will be improving rapidly in quantity, but most importantly in quality. I think that if we have to trade off quantity of qubit versus quality in a few years, it would be interesting and focus on having better qubit rather than more of them. And hybrid algorithm can benefit really incrementally of this improvement in the hardware. The second point is that hybrid algorithm implement basically, we know how to use them to implement data-driven, to solve data-driven tasks. And it's now the time basically to use those as a lab bench to experiment with NISQ devices and to find application-based cases of quantum advantage. Thank you very much.